Welcome back, everyone. So we know at this point how to take a product and turn it into a sum. For example, you've done something like this before where if I said, hey, multiply this thing, 2x plus y times, x minus 6, you could multiply it out, and so this is a product. If I wanted to write it as a sum, well, you would use the distributive property, or perhaps you would use the generic rectangles, and turn it into a sum. A bunch of pieces just added together. So this one would be 2x squared, let's see, minus 12x plus xy minus 6y. And so we're really good at this point. And this process, we would call it multiplying. Multiplying. Nothing too crazy there. What we're going to investigate in the next couple of videos here is how can we go in the reverse direction? How can I take a sum and turn it into a product? That is what factoring is. Factor is a verb. To factor something is to, turn it into factors, the noun. So these two pieces, something times something, well, you call those factors. And so to factor something means to break it up into a bunch of factors, a bunch of things multiplied together. So what we're going to do is, excuse me, we're going to play around with some algebra tiles in this video just to get a feel for what this will look like. Alrighty, so in these, one last bit is that in both of these examples, or in this, what's the word I'm looking for? This model, we call it using the area model, because both of these, they represent the area of a rectangle. Area of a rectangle. The product, rectangle, is simply the base times the height, whereas the sum here is just if you break the rectangle up into a bunch of, little rectangles, which we can see at the algebra tiles over here. So this is also the area of a rectangle. And so the reason they're equal is because they're both the same number. They're both representing the area of a rectangle. Again, it's just a matter of how you're looking at it. And you might prefer the product or the sum based on what you're trying to do. Okay. For us, we would prefer to have it in factored form because that is easier to find the x-intercepts for a quadratic function. Okay. Enough of that. So let's actually just play around. So what I've done here is I come up with 3 problems for you. 3 separate problems. This represents the area of some figure, right? A rectangle if possible. So what we're going to do is we're going to take these tiles and create rectangles, or at least try to. It might not be possible, and we're just going to see. Okay. So right here, I have my 2x squared tiles, 11 x tiles, and 5 1 tiles. Let's just remind ourselves how these algebra tiles work. So kind of the rules of the game here are that the tiles must line up edge to edge, and they must line up exactly. Here's what I mean by that, is that I can't have something like this. I cannot do this because unfortunately the tiles don't quite line up together. You can see a little gap there, or a little extra on this stack here. So also remember, the name of the tile is its area. So since this tile has a name of x, its dimensions are x by 1. Similarly, the 1 tile right here, the little single tile, has dimensions 1 by 1. And the x squared tile has x by x. For this one, since we're going to use negative tiles here, one side on this guy, these are both length 1, but one of them might be negative 1. It actually doesn't matter, but we'll see those in a second here. Same thing with this one. It could be negative x by positive 1, or it might as well also be negative 1 by positive x. But in terms of the actual length, it's the same length here. This lines up like so and like so. Okay? So what I'm going to do is I'm just going to pause the video here, or what you should do is pause the video, and see if you can take these algebra tiles and rearrange them in a rectangle that with everything, all the edges lined up perfectly. Alrighty, so pause the video, and try that on your own. Alrighty, so here are my two rectangles for A and B. So I've taken my two x squared tiles and I've plopped them together right here. I broke up my 11x tiles like so. So I have one up in the corner, so I'll write that as, I'm gonna write that as 1x there. Sorry about that. I'm gonna write that as 1x. And then I have 10 down here in the bottom right, so I have 10x. So I have a total of 11 x's, but I just split them up. And then I have my 5 in the top right there. Okay, so what I'm going to do now is I'm going to write the area of this rectangle as a product now. Again, to do that, I need to know the dimensions of the rectangle and get its base and its height. So since this is an x squared tile, I know that its side lengths are x by x. So I like to draw it like so. There's another x right here, so this is a total 2x tall. And then the 1x, remember that this is x by 1. And so the height of this guy, so again the area. I like to draw the sum in red. I've been using that. That's what I started doing in class because red is also known as scarlet, and scarlet starts with S. So the sum, which is 2x squared plus 11x plus 5, is equal to the product, and I'll use purple for product, equals to the product. Oops, sorry, we missed one more thing here, that this is 1, 2, 3, 4, 5. 2x, because it's x plus 1 times x plus 5. That's all there is to it. And so we'll do this one here, we'll do this one as well. So to get this one, I have a negative x, which is up here in the top right. I have my x squared in the bottom left. Sorry, top left, I have the negative x. Bottom left, I have the x squared. Bottom right, I have my 2 x's. And in the top right, I have my negative 2. So this side will be negative 1 long. And this is x by x. And this right here is plus 2 right there. Okay, now, notice how did I know that this was the case? Because we talked about how the signs on the negative tiles could be kind of iffy. And so the reason I know this is because I know that the x squared tile has to be x times x. Okay, so you might be thinking, well, why couldn't it be negative x by negative x? It actually could be, and you'll see, like, it doesn't matter as long as you're careful about where the signs will all kind of work themselves out. So I am going to kind of hand wave this one a tad right here. I apologize, but in the interest of time, because this video is already a little bit long. So we have the sum here, which is equal to x squared. And we're going to actually collect our like terms here. So this would be plus 2x minus x. And say it'll be plus 1x. And then minus 2. The reason I need to give it to you like this is because you'll see it later. I don't want to kind of spoil the surprise. And we have the product here. X plus 1, or sorry, x plus 2 times x minus 1. Now what about this third one here? So check this out. Let's see, I have my third one, which is down here. So I have, let's get rid of these. We've already done those ones. I have x squared plus 3x and then plus 10. So right now, I don't know if I can actually do this because I can take maybe 3 of them and stack them like that and maybe do some more over here, but I'm still missing a big chunk of my rectangle, right? Even if I did something like this, well, I still have basically too many single tiles. I have a rectangle right there, but I have all this left over. So I don't know about you, but I'm thinking that this might actually not be possible. I don't think I could turn these tiles into a rectangle. At least not using whole numbers, not using integers. And that's, for our purposes for this class, that's enough to say it's not factorable. Okay, so this is actually not factorable. And I'll emphasize right here using whole numbers or integers. It's possible that you could have something that is factorable using not whole numbers, but for us in Algebra 1, we're just going to focus on numbers that are on expressions that are factorable with whole numbers. Okay, so that's all I want to talk about in this video. This is the most interesting thing, because I could give you any random product. I could take two polynomials, put them in parentheses, and have you multiply them, and you'd be able to get a sum out. But what's interesting is that it doesn't always work the other way. You can always turn a product into a sum, but you cannot always turn a sum into a product. Sometimes you can, and sometimes you can't. Alrighty. Thanks for watching. In the next video, we'll make a couple observations about this to actually see how we can start to factor without the algebra tiles.